C'est un plaisir, j'ai invité aujourd'hui Alexi Morin Duchesne. Will talk about fusion in the periodic Temperley-Lieb algebra and connectivity operators of loop models. Okay.
Oh, thank you. So is the mic functioning correctly? I think I can also remove my mask if nobody is close enough to me, right? Yes, okay. All right, so I'm quite happy to be here. This is the first for me also giving this hybrid type seminar. And I'm going to tell you about a recent paper. We put it out just a few weeks ago with Yassine Klef, also in the audience, about fusion in the periodic Temperley-Lieb algebra and connectivity operators for loop models. So, an outline of my talk. So, first I'm going to discuss, maybe this is going to be a review for many members of the audience, lattice models with geometric observables and the periodic Temperley-Lieb algebra. I'll set my conventions so that we all agree with the objects we're working with. And then I'm going to discuss this new way of doing fusion that we defined for standard modules over the periodic Temperley-Lieb algebra. And then eventually I'm going to discuss how these fusion products decompose as sums of irreducibles over this algebra. And then finally, how from this we're able to get the fusion of conformal fields in the underlying logarithmic conformal field theory. Okay, so first, quite well, in the last maybe 20 years, there's been a lot of interest for lattice models that are defined in terms of observables which are non-local and geometric. So there are many examples, but the most studied ones are the ones for percolation, so bond and side percolation. Here my slide will expose what happens for bond percolation. But there's also the easing model in this Fortuin-Castellan expansion, as well as the dimer model. You can take the dimer model, map it to a model of spanning trees, and you also have these geometric observables. And so here I have a configuration of the model of percolation on a subset of Z2. So on the square lattice, I have these edges that can be either occupied by a bridge or unoccupied. Here I'm studying the critical model where they have equal weights. And the partition function here is sort of very simple to compute. It's just the sum of all configurations, and all configurations are given a weight which is equal to 1. And as a result, so this partition function is just the sum of all the configuration, the number of such configuration, which is 2 to the exponent of the number of edges in this diagram. So as a rational model, this is a trivial model. All if I call sigma I and sigma j the various edges, well, they are independent, so they're correlation functions. They trivially factorize as a products. And so the interest behind this model is not local, but rather in the non-local properties of the clusters. So here in my diagram, you see that I've set two positions where two vertices in this graph, which I've drawn, one of them with a green circle, the other one with a purple circle. And the probability PC of xy are the positions here of these two circles. So PC is the probability they lie in the same percolation cluster, namely that I can go from the green one to the purple one by traveling only on the red bridges. And so a known way to tackle this problem is to map this problem to a model of random curves, a so-called dense loop model. I think many of you are familiar with this, where these loop segments, they draw the contours of my percolation clusters. And so this is clearly a bijective map. And if I remove the bridges, well, the question of this probability boils down, it can be understood in terms of the loop segments, right? So I can travel from the green point to the purple point only if I do not cross one of these contours. Okay, so this is well known that this model is now, with its non-local observables, is described with a logarithmic CFT, and in particular, this probability is a two-point function of what we call a connectivity operator, okay, in positions x and y. And of course, CFT tells us that if these are primary fields, they should behave as a power law, and we know how to compute the resulting exponent. This exponent, I believe, was first computed by Nienhuis in the 80s using Coulomb gas arguments. Okay, so in my talk, I'm mostly going to focus on this geometry, the geometry of a cylinder, where I have this loop model defined on the cylinder. I have the two possible tiles, and now these two tiles, they live on the faces. The degrees of freedom live on the faces of my lattice. And of course, my model of percolation here, if I reintroduce my percolation clusters, you see that they live, the percolation sites, they basically live on 1/2 of the vertices, okay? But yeah, so this loop model is sort of more general, and it's defined in terms of a parameter beta, which we take as real. And percolation corresponds to beta equals to 1. So the partition function is, again, the sum over all configurations on this cylinder. And then we have a weight, which is beta, and the exponent is the number of loops in this diagram. Okay, so percolation is beta equals to 1. The Ising model corresponds to square root of 2, and so on. And this model is very rich. You can define a very big family of correlation functions. The first one is precisely these cluster correlators, but maybe now for, yeah, so I can put more than 2 points. Here in this configuration, I put 4 such points. And the question is the same. What's the probability that they all lie in the same cluster, right? So here I can write this like this. So PC depends on the number of positions, ZA, ZB, and so on, is 1 over the partition function, the sum over all configurations. Then I have the weight of the configuration, beta to the n sigma. And then I have a delta function, which is basically 1 if they all lie in the same cluster and 0 otherwise. So this is one type of correlation cluster, but we could be even more general and say, for example, the green point and the orange point, we want them to be in the same cluster, but in a different cluster than the other two, and so on. But yeah, so correlation for clusters. We could also define correlation for loops. So what does this mean? Instead, I move my small disks and put them now not on the vertices but on the edges of this graph, and then I ask the question: are they all on the same loop? Okay, so this is again written in the same way. Well, now the delta function is this LALB means that it's 1 if they're all part of the same loop and 0 otherwise. And maybe even more generally, what I can do is I can define a model where for some of these tiles, in some positions, I leave a set of tiles which are not occupied by the 2 possible choices. And then I put a small circle around here. So there's one here, there's a second one here. And then what I do is I see that around these 2 tiles, I have a number of free loop segments, and I'm going to attach them to the one here and to this circle in the center. Right, so here there are 6 of them, here there are 4 of them. And so this defines a connectivity operator with 2k legs. K is going to be, in this example, an integer. So I have k equals to 2, k equals to 3 for this example, and the one corresponding to loops corresponded to k equals to 1, and corresponding to clusters was k equals to 0. So in general, we're interested in computing this correlation, the correlation function of these connectivity operators with 2k legs. Okay, so I'm going to introduce a set of diagrammatic operators. You'll see that they're going to be related with the periodic Temperley-Lieb algebra, but not elements of this algebra. And these connectivity operators, they're going to look like this. So they're going to be written as O, K, comma, X. K is, it relates to the number of legs. So you see here that this one here would have k equals to 4, and it would have precisely 8 legs. And the one here is k equals to 0. Okay. On top of this, there's a position j. So I'm going to be on some cylinder of perimeter n, and the position j is going to be so the place where this operator is inserted. So for example, here the legs are inserted between j and j plus k minus 1. Yes, and finally there's going to be an extra parameter x, which is a complex parameter, which is going to have a physical meaning defined in the next slides. But if I just go over this quickly, for the first case, when k, I have no legs, this x is going to parameterize loops that encircle this green circle. And here, this x is going to couple to, so we're going to call these eventually defects, or so these legs. And sometimes when we act with the Temperley-Lieb algebra, they're going to cross this dashed line here that I drew between my circle and the point on the perimeter between 1 and n. And whenever they're going to cross, well, the parameter x is going to appear as a twist factor. But we're going to describe this in more details in the upcoming slides. Okay, so of course, we know already the 2-point functions of these connectivity operators. So these 2-point functions given here. So I write this as pk, where k is a number of legs. I have my 2 positions. And as usual in CFT, these are actually primary operators, and then we have a power law behavior, and we know precisely what these exponents are. Okay, so these exponents are written in terms of HRS, the usual formula for the usual Katz formula for for the conformal dimensions. And these are parameterized in terms of b, and b parameterizes the loop weight, beta, as follows. So b is minus 2 cosine pi b squared. Okay, so in terms of b, there's also parameterization for this parameter x as e to the I pi mu. And then we see that, so the h's that appear in this power are h mu comma k and h mu comma minus k. Okay, and finally, of course, the central charge, the well-known value in terms of b. Okay, so this is the general result. These are often called, I believe, watermelon operators. And the values are again known from Coulomb gas calculations. And in particular, the cluster and loop correlators, they correspond to having k equals to 0 leg or k equals to 1 leg and a specific value of this x parameter. So we know exactly how the 2-point functions behave. Now, once we know how the 2-point functions behave, CFT also tells us how the 3-point function behaves. And so the next challenge is computing the 4-point function. And typically for rational CFT, there's a very neat trick to compute these 4-point functions. We look at the representation theory of the Virasoro algebra. We find singular vectors. This gives us a set of, we can translate this in terms of differential equations satisfied by the 4-point function, and then we solve this differential equation. This actually does not work in this case. And the main reason is that, well, this parameter x, it has a value of the corresponding conformal dimension depends continuously on this x, and for most cases, we don't have singular vectors that we can use to derive those differential equations. So instead, the other technique that is used is the conformal bootstrap. And the first step to do this is to, in this 4-point function, to insert a full set of states, right? So a sum over mu, and then the result is, so a sum over mu with a product of two 3-point functions. In order to be able to do this, so we call this a decomposition over some fusion channels, we need to know exactly what values of mu should appear here. So in other words, we need to know how, when we take the fusion of these two fields, of these two connectivity operators, what kind of fields appear here? Like, this should be a direct sum. Is it continuous? Is it discrete? So at the moment so it was unknown exactly which fields occur here. And this question can be translated into fusion for representations over the periodic Temperley-Lieb algebra, which is the question that we're going to address in the next slides. So of course, once we have this, then we can do the conformal bootstraps, compute these numbers either numerically or analytically, and then find the 4-point correlation functions compared to Monte Carlo simulation. And this was done by these two groups, which are represented in the audience. And of course, exactly how this should be done was unknown. So what these two groups did is they made some assumption for how for what fields should appear here on the right-hand side, and then solved to find the resulting 4-point functions. And of course, our objective now is to really understand how to do this fusion, what fields appear in the fusion of these two connectivity operators. And so for this, the correct structure is the Temperley-Lieb algebra. I want to understand how modules over the Temperley-Lieb algebra fuse. So I'm going to tell you what conventions we work on. I'm sure everybody here is familiar with this algebra. So the generators are these Ej, when j runs from 1 to n. Very often they're drawn on the plane. Here I'm going to draw them on an annulus. Okay, so Ej has these half arc connecting j and j plus 1. Likewise En. And then I have these two shifts operators. One shifts to the left, the other one shifts to the right. So I have n of these nodes as usual, and the identity can be obtained by multiplying the omega with omega inverse, and then it's just this diagram. So typically they're drawn on a rectangle where we have periodic boundary conditions on the left and right. And here I've drawn this dashed segment tells me where I should cut in order to get this diagram from this one. Okay, so the product, to get the product of two generators, E1 times E2, we draw E2 inside E1 and then pull the strings. And then if I have a loop, like in this second example, E2 squared, well, I have a loop which is called a contractible loop. I remove it and then I add instead a factor of beta. If I have a loop which actually goes around the inner parameter of my annulus, like in this example here, right? So I have E1, E3, and so on up until En minus 1, E2, E4, and so on up until En. Then I can get a non-contractible loop, and here it's not removed in my algebra. It's just left there, but I cannot remove it. So my algebra is infinite dimensional. I can have arbitrarily many of these non-contractible loops. And in terms of the relations, so these are the defining relations of my algebra. Again, here, for example, this is the one where contractible loops are removed, but there's nothing about non-contractible loops. But these will be important later when in my next slide. So standard modules, again, the representations that have been studied by many, in particular by Gram and Lehrer. They're defined in terms of link states. Again, often they're drawn as planar diagrams. Here I draw them inside disks, right? So n is the number of sides, which you can see here. As the first number k is half the number of legs. So here I have 0 legs or defects connected to my marked point. So I have a marked point in these link states. So here k equals to 1, I have 2 such marked points, and k equals to 2 such marked points. So these are the vector spaces for n equals to 4 for the various possible standard modules. And here I'm going to define also another module that we call the vacuum module, V, where again I have link states, but this time no marked points. Okay, so there are only one for each value of n. There's only one. So V4 and V6 are drawn here. Okay, so these are going to come back in my description of fusion to the next slides. Okay, so the action on a standard module, again, I think most people know this in this audience, but whenever I want to act with an element of Temperley-Lieb, of the periodic Temperley-Lieb, I draw this element around my link state, and then I read I read the connection on the outer perimeter of the new link state, and this gives me this. And in other cases, I will have some prefactors that will appear. So, for example, acting here with E1 on this state would connect the positions 1 and 2, and the result, I would get a weight beta. Okay, it's not a question. Okay, so I have a weight beta. I also have now a weight alpha. So if I act here with E3, I would have a loop that connects these positions 3 and 4, and create a loop where I have this node inside with this marked point inside. And we would remove this weight not with the weight beta, but with the weight alpha, where alpha has a different parameter. And finally, there's also a twist parameter. And this happens whenever the action of an element of the algebra forces one of these defects to cross this dashed segment that connects my marked point to the point on the perimeter between 1 and n. So acting here with omega, I would have this one here crossing the dashed point with this point to its right. And so I would put a factor of z, and if I would cross in the other direction, I would put a factor of 1 over z. Okay, and finally, also important for the standard action, if I act with E2, this here connects 2 defects, and the result is 0. So I cannot decrease the number of defects. So these modules are well studied. One result of Gram and Lehrer is that if you set generic values of q and z, then these modules are irreducibles. Of course, they did a much deeper analysis of these modules. And finally, what happens on my vacuum module, the action of the algebra is defined in the same way. So the only difference being that all loops, so there's no marked point, so all loops that are closed get a weight beta. Okay, so now, of course, we want to know how to take 2 of these modules and fuse them together to form their fusion. And maybe to be inspired about this, I have 2 slides which tell you how this was done for the usual Temperley-Lieb algebra. So not without periodic boundary conditions. In this case, the diagrams are typically drawn on a plane, not on an annulus, and the corresponding connectivity operators they lie at the boundary of the domain. So here I have the loop model defined on a square or rectangular domain, and then I choose a set of consecutive nodes, and instead of attaching them to a circle like I did before, I just draw these. I draw them as defects with different colors, and in the resulting configurations will have a weight which is non-zero, only if all of these defects are actually tied to, like the green defect cannot be a green defect cannot be tied to another green defect. It has to be tied either to a purple one or to an orange one. Okay, and so to each of these connectivity operators is associated a representation, a standard module over the usual Temperley-Lieb algebra, and this now their fusion has been studied by multiple groups: Piers Rasmussen in 2006, Riedenzeller 2007, and then more recently Ganutina Vassa in 2012. And so the idea is to start with 2 standard modules, and to describe the fusion, we define a new representation. So here, VKL, where the number of nodes is NA plus NB, and then this representation will depend on these 2 numbers K and L, which are the number of legs. So here, 3 legs, K is equal to 3 halves. k equals to 1 corresponds to 2 legs, and so on. And so there are two ways to describe this fusion, these new representations VKL. The first is purely diagrammatic. So you define a representation. That has, so it depends. Here I have k equals to 1/2 in my example, and L equals to 1 on 5, n is equal to 5. So I have these link states with 5 nodes. And then I have defects. So I can either have one green defect and then 2 purple ones, or just 1 purple one. And the action of the algebra on these states is as follows. So for example, here E4 acting on this first state would connect together 2 purple defects, and that would give me 0. And then E3 acting on the same state would connect a green defect with the purple one, and then these would just be removed with the weight 1 instead of 0. And so in total here I have a representation which has a size 9. The other way of defining this is algebraic. So we use the fact that this tensor product TL&A, TL&B is included in TL&A plus NB, where here the tensor product simply means that I have 2 diagrams and I attach them together. Okay? And this fused representation, you start with the tensor product of the 2 standard modules, and then you act on it with Temperley-Lieb on NA plus NB sides, but in between there's some sort of selective tensor product. And what this means is that if you act with an element of this algebra, this element will only be able to go through this sort of filter if it belongs to this subalgebra of the larger algebra. Okay? So again, I can draw my basis in this. I can find my basis for my example. K equals to 1/2. L equals to 1. Again, I have these 9 states. You see that they look a bit different than what I had for the diagrammatic definition, but there's actually a very clear bijection between the two. For example, this one here maps to this one here. You just have to glue them together. And so in the end, these 2 definitions are equivalent. And for my example, you can find that, so this representation of dimension 9, if you set beta to be a generic value, it's going to decompose as a direct sum of the 2 standard modules, okay? And the general result of the fusion, well, it's again a decomposition with a number of these irreducible standard modules for generic values of beta. So now, this brings us to what happens in the periodic case, right? In the periodic case, it's sort of less obvious because you want to fuse diagrams which are defined on an annulus. And it's not exactly clear how you should do this precisely. And in fact, this problem was tackled already. There were 2 proposals for the fusion in the periodic case, one of them by Ganutinov-Seller with the second paper with Jacobsen. And then there was a second proposal by Jonathan Beltet and Yvan Saint-Aubin. And these 2 proposals, they actually turn out to be inequivalent. So they're inequivalent. And also, it's not clear that the correct way of doing fusion if you want to compute correlation functions for these connectivity operators. So here with Yasenikov, we came up with a new idea, with a new proposal, which is the following. So we define a new representation, right, which is the fused representation. So fusing WKX and WLY. So of course, this new representation depends on K and L, the number of legs that we had in the 2 standard modules. The parameters X and Y. Okay, and then a new parameter Z. Right, this parameter Z, we'll see what it means in a second, but we understand it as a parameter that describes the channel in this fusion. Okay, and in order to construct the tensor product of these 2 states, so we're going to do it as following. So we're going to draw like a bigger disk, which involves here, so the first one has 5 nodes, n equals to 5, and b equals to 6. It will have 11 nodes, which is the sum of the 2. And then in this disk are going to be drawn both link states. So the positions 1 to 5 have the exact same connectivities as those in the first link state. And then 6 to 11 have the same connectivities as the second state. Okay? So in general, we're going to consider representations that, in contrast with the standard modules, they don't have just one of these marked points. They're going to have 2 of them, right? And we're going to write them as A and B. And these A and Bs, they're going to be, like in this first example, there are going to be no defects, but there are going to be cases where they're going to have a number of defects. Okay, and so the different representations X, okay, are going to be characterized by the numbers of defects attached to A and B. And the other nodes will be connected by loop segments that can travel to the left or right of B. Okay, so You see here that in my three examples, I have n equals to 12. This is a number of sides. I've also written at this point, I've called it C, between this 1 and n, and I've drawn two dash segments between A and B. This is going to be important in the next slide. And then, yeah, so and then I have these through arcs and I have defects. So in the next slides, I'm actually going to describe these modules and split the description in three cases. The first one is when both A and B have no defects. The second one is when A has some defects but B does not. And the third one is when A and B can have a non-zero number of defects. So I start with the first case. So K and L are equals to 0. Okay, so here I drew all the states in one example when n is equal to 4. Okay, so I draw all the possible states where, again, the points A and B there are no defects, and then the points A and B can be in arbitrary positions, in arbitrary areas delimited by these blue segments. And when you do this, you see that you have precisely 18 states that appear. Okay, so how did I order them? You see that on the first line, there are what we call through arcs. So these are arcs that travel between A and B. So here there are 2. Here there's only 1, right? And only 1 for the states on the second line. And then on the third line we have 0. Okay, so this number is going to play an important role. Okay, so how does the algebra act now on these states? Well, the action is the same. If we want to compute E3 on this state, we should draw like a big circle here with E3. E3 would connect together points 3 and 4, and then we read the new link state from the outside perimeter. In doing so, in this first example, what we see is we produce a loop which surrounds the green mark point, and this one is given weight alpha A. If it surrounds the purple mark point, like in this example here, I act with E2, E4 on this state. This would connect together the points 2 and 3, as well as the point 1 and 4. So I would have a loop with this mark point inside. I give it the weight alpha B. And finally, in this third example, I can also have loops that surround both marked points. So acting with E2 here, I would close here, I would attach a loop segment to 2 and 3, and I give this a loop alpha AB. And finally, if I can also produce loops that encircle none of the marked points, like in this example here, 2 and 1 would be connected when I act with E1, then this just produces a weight beta as usual. So I have 3 parameters, and these 3 parameters are parameterized in terms of of x, y, and z, which are the 3 parameters here, the 3 complex parameters defining my representation. Okay, so this was the first case, k equals to L equals to 0. I also have, so now the second case is when L is equal to 0 and k is larger to 0. So in this case here, what I see is that now these are all the link states for n equals to 4, k is equal to 1, and L is equal to 0. I have 8 such states. So 2 defects. I have, again, 2 marked nodes. The first one, the green one, has 2 defects. And what you see here, so maybe something subtle, is that this red point can sort of be anywhere delimited by this. So you can be to the left or to the right of this curve. But for example, if you look at this one here, there is no state where this red dot is here, is in this area. And the reason is that these 2 states, where this one here and the one where the red dot would be here, would be identified up to a twist factor. So I'm going to describe this, I'm going to describe this now. But here, I would have precisely 8 such states. Again, the action of the algebra is the same. I draw my elements of the periodic Temperley-Lieb algebra around, and then I look at the resulting link state. Then I can produce various weights. So the first thing that I can produce is, again, I can produce a loop here acting with E3 that surrounds this red node here. This would be given a weight alpha B, where alpha B is y plus y inverse, right? This y here. If I act with something like in this last example here with E4, this would produce so I would connect together points 4 and 1. This would connect together 2 points attached to the same node, and this results in 0, like it would for a usual standard module. So this would be 0. And so this also means that I cannot have a loop that surrounds, like if I would produce a loop that goes around my green point, then this would have a weight 0. So there's no alpha A in this example. So 2 other parameters, x and z, what they do is they actually, again, they couple to the winding of defects, like, and then how they cross these 2 dashed lines. And so here I gave some examples. For example, E1, if I act with E1 here, I connect the point 2 and 1, and we see that this defect would cross this line between the point A and the point on the perimeter, and this would produce a parameter C, parameter X. If it crosses here in this example, here I would act with E2, so I would have a loop attaching positions 3 and 2. It would cross the other dashed line and now produce a way that depends on Z. And here I have a third example where it actually crosses both of them. And then it would produce, again, a way that depends on C. So I've decided to give maybe a more clear description of exactly how this works, how exactly we assign twist factors. And so they're assigned as follows. So here I have the 6 examples. So when I have a diagram where I have a defect that crosses this dashed line, so the dashed line between A and this point that I called C, if going from this point A to the perimeter, I cross this line with the point, the green point to its right, it produces a factor of x. But if it does so with the green point to its left, it produces the factor 1 over x. This is sort of the same thing we had for the standard modules. Now, in the second example, now this defect attached to the green point, it now crosses the line attached from B to C. If it does so with this point to its right, we give a weight, so z divided by x. Right? So, and if we do it in the other way, where now it crosses it with the point B to its left, where it's 1 over this weight, so x divided by z. And finally, I have, in this last example, if it crosses both, well, it actually turns out to be the product of the two above weights, so x times z divided by x, and the result is just z. Okay? And likewise, if it crosses it in the other direction, then we have 1 over z. Okay, so this is how, in general, twist factors are included in this definition. So now I'm moving on to the third case. The third case is when both A and B have a non-zero number of defects. Again, my example for n equals to 4, k is equal to a half, L is equal to a half. So what we see in this example, again, we have 18 states. And similar to what we had for the usual Temperley-Lieb algebras, here we're going to have K and L can have, A and B can have 1 defect, but these can actually connect and produce states that have 0 defects. So in total, I'm considering a vector space where my link states have a number of defects attached to A and B that can vary with this number R, right? So here in this example, that's sort of a simple example. It can be 1 defect or 0 defect, but if I had, say, 3 and 2, 3 defects and 2 defects, then they could reduce to having 2 and 1, and then 1 and 0, and so on. Okay? The action of the algebra is again the same. Now we have weights alpha AB. Again, if there are some cases like this one here where E2 acting here will produce a loop that encloses both marked points. So we give this a weight alpha AB, where alpha AB is Z plus C inverse. And then we also have some twist factors that will depend on X, Y, and Z. Okay, so I'm not going to describe this in more detail. I've gone over this for the previous case, but you can go in our paper to see exactly how this is done. And so in this example here, yeah, so E3 would connect 3 and 4, so we see that we would have a defect crossing this line, given a parameter 1 over X, a twist factor 1 over Y, sorry. And so maybe, yeah, so the prominent feature of this representation now is that I can connect these defects and this gives me a non-zero result. So acting with E4 here would create a loop that attaches these 2 points 1 and 4, and then the number of defects would be reduced, and I would have a factor here that depends non-trivially on the twist parameters X, Y, and Z. Okay, so this is how these representations are defined, and of course now we study these representations to understand how they decompose. And here, this slide gives you a number of its properties. So the first is that, again, link states have a number of through arcs, right? Remember, the number of through arcs, we call the depth. We usually write it as P. And so this link state has P equals to 2. This here has P equals to 1, and P equals to 0, the number of arcs that separate the green and purple point. Clearly, the action of the algebra can only decrease this depth. Right? So it can only reduce a number of through arcs. It can decrease it, it can keep it constant, but it can never increase this number. So in particular, in my previous examples, this means that, yeah, so acting with algebra, I can, on a state like this, I can stay inside this, or I can move, I can go down I can go down these lines. I can produce states that have a smaller depth. Okay, so the depth is not the only important number, but also whenever K and L are bigger than 0, the other number that can only decrease and that may not increase is the total number of defects, right? So if I have these two defects, I can connect them together, but the action of the algebra cannot increase this number of defects. Okay, so this is important because this gives us a partial decomposition of our representation. So it allows us to define a filtration of modules and to say that, for example, if I go back to this example here, so here this would be, on the last line, this would be a submodule. And then if I considered only the states on the first two lines, this would be a bigger submodule where the first one is included, and then the full module. So this defines the filtration, which gives me part of the decomposition of these modules. So a second important property is cyclicity. So the way that we define these representations, they're such that they can be generated by the action of the periodic Temperley-Lieb algebra acting on the states of maximal depth. In other words, if I look at what happened on the first line and act with the algebra, I can produce everything in this. In these representations. Okay. Oh, sorry. And then the dimension. So I showed examples where I had dimensions 18, 8, and 18. But we actually have formulas for these dimensions. And the first formula that we derive is in terms of sums of dimensions of the standard module. These, of course, the dimension of a standard module is known. It's a simple binomial. And here we have a sum over such dimensions with some degeneracies. And the idea to show this is rather simple. We can take an object like this one, and we're going to map it to a link state in a standard module. And we're going to do so in the following way. We're going to draw a small bridge that covers the two marked points, the two colored marked points, and all the loop segments that connect to them. And we're going to interpret this in terms of a single marked point in a standard module. So here you would see that I would have one such marked point with 4 defects in this first example. Likewise here, and this one will have 2 defects. And then we can map this to a link state of a standard module. Okay. In doing so, if we apply this idea to all states, for example here, what we see is that the same states, the same standard modules would appear with certain degeneracies. Like for example, all 4 of these states would be mapped to this same state here, which is the reason for this 2m here. So we have an explicit formula for the dimension, and then it's a simple exercise to resum this and find this simpler equation. But actually, this here actually turns out to be useful. Of course, this does not tell us how the module decomposes because the dimension of the standard module did not depend on z. But this, when we look at the decomposition, this will actually, this will be useful. So before I move on to these decompositions, I want to tell you how these standard modules are related with connectivity operators. The operators that I found earlier like this, right? They were these objects O, K, X, the J was the position, K, I had 2K legs, and X was this complex parameter for the weight of the loop surrounding this, or the way that it couples to the defects crossing this dashed line. Okay, so these connectivity operators, clearly they're not elements of my Temperley-Lieb algebra. They have they have a marked point, they have these legs. So they're not an element of my Temperley-Lieb algebra, but I can still understand how they act on the diagrammatic action on link states. So here, this example here shows you how it acts on the vacuum module. So the vacuum module where link states had no marked nodes. When I act with a connectivity operator on such an object, well, it's the same, right? I draw this connectivity operator around it, and then I read the result on the outside perimeter. Here, I insert such an operator in position 1, right? Position 1, and then it has k equals to 1. So k equals to 1 means that it has this one here would have just one. It would be connected by 1 point to the inside or 1 point to the outside. And when I do this, I obtain a state which looks like this, and which is actually a state in a standard module. So, okay, so a second example is given here. Now, again, I act in position 1, but now I have instead of having just 2 legs, I'm going to have 4 legs, and I get a different standard module which has now 4 legs. And so the idea here is that these connectivity operators, defined as these diagrams, you can understand them as acting on the vacuum module, and the result is they give us standard modules. Here, it's not exactly what I wrote here is an O hat, so it's a dressed connectivity operator, and it's dressed by including an element of the periodic Temperley-Lieb algebra to the left and to the right. So these are some elements. And of course here we put the position 1, but it could have been arbitrary position. For example, if A is omega and B is omega inverse, then the result that you get is just OKX with a position shifted by 1. So in other words, this is a very nice way of understanding a standard module in terms of the action of a connectivity operator acting on the vacuum module. We can continue further and then see how they act on standard modules. So now I have connectivity operator acting on a link state that belongs to a standard module, which already has one of these marked nodes. If I do so here I chose k equals to 0, so I'm going to have 0 legs acting in position 2, and this turns out to add one of these connectivity operators here between 2 and 3. And the result is a state in a representation x. Likewise, if in this second example, I'm going to have k equals to 1, so 2 legs, I insert it in position 2, and then I get this new link state which belongs to some representation x with k equals to 1 and L equals to 1. So the idea is that now a connectivity operator acting on the standard module will now produce the representation x that I spent some time defining in the previous slides. Okay, so now, of course, now we know that this one can itself be defined in terms of an address connectivity operator acting on the vacuum. So I can write these representation x as a product of two address connectivity operators acting on the vacuum. And so for us, this is a strong argument to convince ourselves that these representations, they really correspond to doing the fusion of two connectivity operators, right? So they correspond to the action of two addressed such operators acting on the vacuum module. Okay, so yes?
I have a question. A and B here can be anything in the Temperley-Lieb algebra and browse on them? Or?
And anything in the Temperley-Lieb algebra and?
You browse them, that is, you consider all possible.
Yes, exactly. So of course,
it's a big thing.
it's exactly. It's a big set of elements. So it's basically this one here, where we allow for all of these points and all these points to be connected arbitrarily. Yeah. So yes, it's indeed a big thing. Okay. So now, an important part of this talk is about how these modules decompose. Okay, so we've defined these large modules. They have dimensions that I gave 2 slides ago. And so we studied the decompositions, and we found the following result. So here, Q and Z are generic. So Q beta is minus Q minus 1 over Q. Z is this third parameter chosen generically. And then here we chose K to be larger or equal to L. Then we find that this representation X, it decomposes as this complicated direct sum. So we have one first irreducible module. These are all irreducible standard modules. And then the second part has a double sum of standard modules. And you see that in the double sum, the first number m, which is the number of legs, varies between k minus l plus 1 and n over 2. And then the parameter z here is replaced by z to the k minus l divided by m, and then a phase, e to the I pi n divided by m. Okay, so this is when k is larger or equal to L. If you're wondering what happens if k is smaller than L, well, we also have this relation, right? So when k is, again, bigger or equal to L, you can show that it's actually isomorphic to, you can interchange L and k, interchange x and y, and change z for 1 over z. So this gives us the full decomposition of these modules for generic values of q and z. And so one word here on the strategy behind our proof of this theorem. It's actually rather simple. We look at 2 central elements, so f and f bar, sometimes called, so they're related to the braid limit of the transfer matrix. Okay, so these are, again, elements of my periodic Temperley-Lieb algebra, where every time I have a crossing, I replace it by this linear combination of the 2 possible tiles with weights q to the square root of q and 1 over square root of q, where, again, beta is minus q minus 1 over q. Okay, and so these are 2 central elements, and in particular, their eigenvalues are characteristics of these standard modules. Okay, and what we had to do is to look at all the possible eigenvalues that appeared in X, see that we had precisely this appearing as a submodule, and this actually turns out to exhaust the dimension. And here you can see that when I have the formula for the dimensions, if I go back to it, so it's a few slides ago here, we see that here, this formula here is directly reminiscent of what we have for the module decomposition, right? So here you actually happen to have, if you don't look at this argument here, you have 2m standard modules which have a first label, which is a first index, which is m. Okay, so we're able to understand this in terms of only the eigenvalues of these 2 operators. These modules, they turn out all to have different eigenvalues. Okay, so now that we have this information, we want to go back to the physics. We want to go.
Technical question. Can you explain quickly why for wk minus l you have only one value of z, and as soon as the number of legs is larger, you're allowing all the values? in your sum at k minus L, you have only one z, and when you start at k plus L plus 1 minus L plus 1,
Yes, okay, so,
the sum over n.
okay, so I think I understand your question. So if I go back to this example here, okay, so, or maybe even easier is this example here, right? In this example here, of course, we have a submodule here which is of dimension 6. The submodule is precisely isomorphic to a standard module which would be called W, 0, comma, and then Z, right? So this is what you see here is that it would be isomorphic to a standard module where this alpha AB would just be alpha, right? It would just be alpha. So this explains why the first term is just W k minus L, here k minus L is 0, and then the weight of the contractible loop is just Z plus the inverse. I have only one. Now, of course, let's go to the top part, the top one. Of course, I can consider a module which involves everything, but I can consider a module where I take everything and then I quotient out by this part here. Okay? When I quotient out by this part here, I have something which has only dimension 4. And now imagine that I act with F, the operator F. The operator F, of course, it's a sum of a lot of diagrams, but many of these diagrams, what they will do is they will reduce actually the number of through arcs. If they reduce the number of through arcs, this would sort of produce something in this submodule, and I'm considering now the quotient, right? So anything that has an EJ in there actually vanishes. So if I act with F on this quotient module, as I decompose F into its various sum of diagrams, the only two diagrams that come up are omega and omega inverse, the shifts. Okay, so if I look at just these four states, the action of F, it acts precisely as basically the shift plus the inverse shift. Okay, and so in the end, we can instead of so we can start with this and make a transformation of the basis where we get eigenvalues of the shift, right? So this would be, so you see that this one here, if I rotate it by, if I act the shift operator, I will get this one. If I act the shift operator again, I will get this one, and then I will get this one. So we can define these eigenstates of the shift operators, and as the result, F will act as a constant on these eigenstates of omega, and then it will have the eigenvalues of omega will be the values of the shift, which are these phases, e to the I pi something. And then if I go back here in my direct sum decomposition, so of course I showed you here that when I had the sum module at the very bottom, this reproduced this state. And the second case that I explained was what happened when m is equal to n over 2, which is at the very top. And then I obtain a decomposition where in this example here I have one-dimensional submodules, and I know, and these phases here are related to the different eigenvalues of the shift. Does this answer your question?
Well, I wouldn't call it intuitive.
It's not intuitive, but
no offense meant, but yeah.
Yeah. So indeed, it requires maybe doing the precise calculation, but yes.
Because in the end, it's so simple, right?
I agree. It's very similar.
Allowing all the numbers of length with all the possible phases.
Yeah.
Except some specific points which are very interesting.
Okay, so from this we want to go back to the correlation functions, so the 4-point functions, and to our physical system. So here we considered a 4-point function, which is not fully general. We have a product of 4 such connectivity operators in 4 different positions, but we select, so for 2 of them we put k and x, and for 2 of them we put l and y. Okay, and we're going to select a very physical situation where all twist factors are set to 1. Like if some of these wrap around, we're not going to care about this. And then we're going to choose that any loops that goes around one of these points, so 1, 2, or 3 of these points, it's going to have a weight alpha, which is z plus z inverse. So once of course, the loop model is very rich, and now we're sort of focusing on certain correlation functions in particular, but the richness of the model means that I could make different choices here. But here I'm making a very specific choice. When we take our results and apply them to this particular physical situation, what we find is that we find a set of fusion rules which are closed. And again, this result is when beta and z are generic. This is not written here, but beta, so q and z are generic. So it turns out that, for example, when I fuse W0z with W0z with our previous result, I get this direct sum, W0z, and then the direct sum with some WK with some phases, okay? And so I have a second kind of operators that show up, and I need to know how this operator fuses with the ones with the ones that I've already defined and among each other. So in total, I have only two such operators, and I want to know how they fuse among another. And then our results tell us precisely how this works. And these are all irreducible modules of the Temperley-Lieb algebra, and this all gives us something which is closed. Okay. And so once we have this, we can apply this directly to the 4-point function. So first, we know that if we look at a given standard module, we know how in the scaling limit it decomposes as representations over Virasoro cross Virasoro bar over this algebra. Okay, and here these are modules over the Virasoro bar algebra in terms of the conformal dimensions. In terms of the conformal dimensions, and so the h and h bar. Okay, so here the value of z is parameterized as e to the I pi lambda. So we know this decomposition for the two kinds of modules that appeared in my fusion in my fusion relation on the previous slide. Okay, and so in the scaling limit, of course, there's a direct correspondence between this operator and my standard module. We know that in the scaling limit, this operator will scale to a field which is the sort of dominant field, the one that has the smallest conformal weight. Okay, and the conformal weights are precisely these. Okay, so actually this here should be, I think it should be a plus k. So again, now we understand now how to fuse the two connectivity operators, and we can use this for this correlation function. So this correlation function scales to a correlation function of a product of 4 such fields phi. Okay, and then we can take this, insert the sum over mu's that was given in one of my first slides, and this sum over mu's now is done in such a way that is consistent with the result of my fusion. Okay, so then this gives me contributions from, this is the contribution from for example, from this one here, and then I have a second contribution with a double sum over over the standard modules that appear in this double sum. Okay, so the difference is a bit different if k is equal to L and k is different from L, because we had to use different kinds of fusion here. But the result is, so we get these decompositions. And then, of course, this is a contribution along some standard module W0, Z, which itself decomposes as a direct sum of representations over the Virasoro algebra. So this one, again, will then become a sum. And then from this, we can read out directly the value, the fusion rules, which are like this. Right? So this tells us as the fusion of two fields. Again, it's different if the number of legs is the same or not the same. So here you have a k and a k and a k and an L. And so we find the first one is a single sum, right? So basically this came from this term where we inserted this this sum here. So we have a single sum where p runs from minus infinity to plus infinity, and then a double sum. Okay, and likewise, if k is different from L, the only difference is that here, so we have a mu plus p or just a p, and then k minus L. So this is quite nice because once we have this, what we see is that in this decomposition, in this double sum, we have p divided by m, and these are fractions. So it's a fractional Katz number. Okay, and this p and m they grow to infinity. So this means that we actually have these fractional Katz indices with arbitrarily large denominators. And this is precisely sort of what is expected. We expect that in this fusion, what will appear are all the fields that appear in the spectra that you can see on the torus partition function, which was found in this paper by Di Francesco, Solar, and Zuber. Okay. So.
Two small questions about this.
Yes.
So what are the values of k or m? Are they integer or half integer?
K can be integer or half integer.
Because in your article it seems it has to be integer.
No. So you can consider these numbers to be half integers, and whenever you do representation theory of the periodic Temperley-Lieb, you do find that both integer and half integer appear. When we applied it to the physical situation, when we applied it to the physical situation of this loop model, well, here we sort of we sort of, I mean, our result for the decomposition work, our results here, they stand when k and l are integer or half integer. But when we started looking at the physical correlators, then the way that we define them, they always have an even number of such lengths. So in this case, indeed, the last result here is when k and l are integers. Yes, you could generalize this to half integers. Yes, so indeed, if you had correlators, it depends how exactly you would define them. So how would you define correlators in the loop model if I go to the very beginning, right? So how would you define, you would have to, I mean, we have not made sense of for now, of connectivity operators that have an odd number of points attached to these nodes, but there's potentially a way of doing this which we have not studied. You had a second question.
Yeah, still on your formula, on the first fusion formula, where the right-hand side doesn't really depend on the parameters mu and lambda, right? It depends only on
Yes,
k and l.
that's correct. And this is also something that we found surprising. And this, so you're talking about what happens but this actually, this actually comes from what we found for the Temperley-Lieb algebra, for the fusion of these representations. And you see here that the parameter x and y, they do not appear on the right-hand side.
No, that's not so, well, that's okay.
And
that's not exactly the question. I mean, there's just one detail that it seems you get the generic representation, or if you want to get the identity representation, also irrespective of lambda and mu. So the first term in the first line here is sum over p here, right?
Yeah, so mu here again is something which is it's a constant, yes, but it's not zero, right? It's not necessarily an integer. It's related to the value of z, so it's related to the weight of, for example, for when if k and if k is equal to 0, it's related to the weights that surround both points. This was called alpha ab, which is z plus z inverse, and z is e to the I pi mu.
Yeah, but so am I correct to interpret this first term as essentially the contribution of degenerate representations of the Virasoro algebra?
Say that again?
This first term, does it correspond to degenerate representations of the Virasoro algebra?
I don't think so, because this mu is a variable which is not, I mean, this is a continuous parameter, right? As you vary z, this mu varies, and then it will not have any singular vectors. This will correspond to a module over vir cross bar vir, where we'll have h. Okay, so here it's lambda, right? H lambda comma h lambda. And for lambda, a continuous parameter, you don't have, this is not the identity.
But then the identity is never.
No, that's not quite true. The entity does appear, for example, if precisely this mu is equal to 0. And in fact, so of course, this parameter z is so in other places when we were on the lattice, we would say that this cross would have a small z. We understand it as a fusion channel. So as we argue in the paper, imagine that we want to use these fusion rules to compute these correlators. Of course. Okay, so here we take an example where, again, loops that encircle 1, 2, or 3 points have the weight z plus z inverse. But if they did encircle all 4 points, then it would be identical to having a loop which is like a contractible, and it would have a weight, beta, minus q inverse. So this here is a situation where I have 2 such objects, and when I fuse them, I want that, okay, so a loop that surrounds me, the first one is z plus 1 over z. Likewise, for this one, z plus 1 over z. And then when I get them together, I want the result to be z plus 1 over z. So when I fuse them, I need to put precisely this on the right-hand side, right? I want that loop surrounding, this is what this tells us. Loop surrounding both of them will have precisely the weight z plus 1 over z. But if I went further and then fused again, and then produced something that surrounded all my 4 points, I would have to replace this by w0 comma minus q. Imagine I have a 2-point function, only a 2-point function. In this case, when I fuse, of course, I want that 1 point has a weight, around 1 point the loops have weight z plus 1 over z, likewise around the second, but around both of them, now they should have a weight beta. So if I'm considering a 2-point function, I should change this to w0 comma z cross w0 comma z is equal to w0 comma minus q. And the identity will appear here in this minus q. So in other words, yeah, so So the identity does appear correctly, I believe, in these fusion rules. So yeah.
So, but, yeah, I would expect its appearance to depend on the values of lambda and mu.
In it of lambda and nu, and the reason is it does not. So again, imagine you have a physical situation where you have 2 points. You have values of loops that surround the first point and the second, and the appearance of the identity only depends on the value of the loops that surround both points. They do not depend on lambda and nu. So they depend only on this mu, and this mu has to be set. It's like for a 2-point function, I need to set this mu to be equal to. Okay, so I need e to the I pi mu to be equal to minus q. So I need to set mu to some specific value, in which case the identity will appear.
Can I add a comment? Maybe this case where the identity or other zero degenerate field would appear in the right-hand side correspond to what we call non-generic values of Z. Z is this additional parameter that we have representation. And most of what Alexi has presented here is from generic values of Z. So we avoid this more difficult question. We have studied one case, non-generic value of Z. It's when both K and L equal zero. Here I do most of this work. It's talking non-generic case. But indeed, it's a very important question.
But what is Z again for the
So it's on the lattice. So the idea is that to approach these two connectivity operators, in principle, you have a choice to define the weight of loops which surround the pair of loops. It's not defined by the internal parameters of these operators. So it's something you put, some additional data you put by hand. No, you can put any parameter you like.
So in your fusion, you decide, like you said, that when you bring 2 points, whatever the weight of the loops surrounding both points are trivial, and they're having the usual weight.
No, they're not trivial. They are this Z plus Z inverse. If they have the trivial weight, then it would be the non-generic situation where it's trouble. I mean, the decomposition is no longer direct. So
Yeah.
So in fact, it's not the complete story. Probably the most important stuff for CFT is not yet studied.
Okay, so yes.
So when we study these 4-point correlation functions of Temperley-Lieb operators, we find that the model has some parity constraints on the numbers called K and L. So we find that typically we have even.
Okay, so can you say it again? You find parity constraints. So imagine that I have a 4-point function like this one. The parity constraint is on, or maybe I go back here. I find a 4-point function like this one. What are exactly the parity constraints?
Okay, so the parity, suppose that you consider 4-point functions such that either all 4 points are in the same cluster,
Yeah.
or 2 by 2 they are in the same clusters. Then it's found that the values of K corresponding to the number of clusters that we effectively propagate in the S channel.
That's the same.
Yeah, I think also. Yeah, I agree. I think. Yeah, so I think this occurs in this formula indeed. So if k and l are integers, the resulting numbers that appear here will also be integers, right? K minus l will be an integer, and m will be an integer, and as a result, the number of legs will be even. If k is an integer, but l is half an integer, this will be half integer, and this will be half integer.
Even number of legs, it's 4 times an integer.
Okay, so okay, so I think I was reaching my conclusion slide, my overview slide. So an overview of what I described is we gave a new construction for fusion of standard modules over the enlarged periodic Temperley-Lieb algebra, and we took these new representations and these representations X, and we found their module decompositions when Q and Z were generic. And we argued that these were actually useful to compute correlation functions of the connectivity operators, these 4-point functions, and we were able to find fusion of the resulting fusion of the conformal fields had these Katz integers, which were fractions with arbitrarily large denominators, which were consistent with the known spectra of the CFT, of the expected logarithmic CFT. And maybe two things I didn't talk about. The first is that our fusion is quite different from the two previous proposals from fusion, not only in their construction, but also when you look at how they decompose in terms of sums in terms of direct sums of irreducible modules, so the results are rather different. And finally, like was said earlier, we also study the case where Q is generic and Z is not generic. So sometimes it's called a partially degenerate case when Z is Q to some integer. And in this case, what we find is that the fused module, again, they decompose as a direct sum, and then some of the indecomposable representations are reducible and have these rank 2 Jordan cells for the rank 2 Jordan cells for the transfer matrix and for the braid transfer matrix. So this is quite consistent with the fact that the underlying CFT is logarithmic. So we see these Jordan cells directly. So this is the end of my talk. Thank you.
Kind of a follow-up to what I was asking. You only focused on integer KML, so can't you just take an odd number of sides? What would change if you really had a connected at one vector?
Okay, so if we have an odd number of sides, clearly we need to change the boundary condition. We need to have maybe we need to have a defect at the edge, and this would sort of mean that we would have correlation functions that mix sort of boundary and bulk correlation functions. So indeed, you would have an odd number of legs on the boundary. I still don't see how this would produce a connectivity operator in the bulk that has an odd number of legs. Say that again?
If you then add another one that is not number of legs, that is connected together, and you get back to the edge.
Yeah. Okay. So I failed to see how this would work. This would mean that at somewhere in your bulk you would have. Okay. So for example, you would put at some position. Yeah. I still struggle to find a situation on this square lattice where you would need to have like one of these arcs that has an empty end. And then, typically if you have one of those, the way the model is defined, you would have a second one which is nearby. And if it's not directly next to it, but in principle, what we did should apply to this situation. We have not considered this, but it should work for this situation.
Okay, so everything goes through the combination.
I expect so, but I don't have the precise idea of exactly how you want to construct this. But I think, yes, everything will go through. Our analysis of the module decompositions, everything works correctly, and then you would have to apply our fusion rules to the specific physical situation you're interested in, and then it would work also for half integers.
When
Yes?
you first discussed fusion and the open case, it's 9-dimensional multiplicity. You have these Krigman and Purple lines. And so for this construction, you can take the two small algebras and you can embed them into the big one.
Yes, here.
And that was an important ingredient that we did not with all. So now, when you go to the periodic case, and the proposal that we tried to promote, we were trying also to embed the generators of the small periodic systems into the big periodic system. And I have the impression that you somehow completely avoid doing that.
So yes, so I actually prepared an extra slide at the end about this, and we did comment this in our paper. The answer is, I feel that at the moment we don't have a precise, a complete understanding of this, but we have a guess for what the answer is. So, okay, so in our paper we define what we call a grouping operator, which is precisely this action of taking two linked states and grouping them together into a simple linked state. And of course, the question that you raised, indeed, in your proposal, what you did is you said, we want to find a way to construct two copies of the periodic Temperley-Lieb algebra into one copy, and then you use the Braille translation to do this. Here, we do not use this. So here, so one way of doing this construction is to see this tensor product of two standard modules as a representation, not over this object, but just as a representation over. I mean, you can take one standard module and see it as a representation, one standard module of the periodic case, and see it as a representation of just the usual Temperley-Lieb algebra, right? The second copy is the same, and then you can take this tensor product, which is defined like this, and see it as a representation over this tensor product of Temperley-Lieb algebras, right? So in particular, you see what we did here is imagine that now I have this gluing which glues the left part and the right part together in this way, and I act with it with some generator EJ. Right, so if I act with it with E1, well, clearly E1 will connect these two nodes, and then it will also connect. I can see it as acting on the first state. So in other words, EJ acting on the gluing of UA of two states UA and UB. If EJ is in this range, then I can actually put the EJ inside and act it on the first argument. Likewise, if I have an EJ here, I can have it act on the second argument, UB, right? If it's NA plus J and J is in this range, okay? And this uses precisely this inclusion that I have TLNA cross TLNB, which is a subalgebra of the periodic Temperley-Lieb algebra. Of course, now the question is, what happens when you act with the other ones? Like if I act with E and A, like if I would act between 4 and 5, okay, then with E, yeah, so E4 in this case, I cannot have this act on either UA or UB. I cannot move through. So this is a bit like having the selective tensor product for the usual fusion of the usual ordinary Temperley-Lieb algebra. So the way that we understand this now is that we say, okay, so this map, this gluing operator, not only does it produce like the tensor product, but it also assigns it like the structure of a standard module WKZ. What does this mean? It means that now, of course, I can act with some generators, and I could produce, for example, non-contractible loops, and this would have to be removed. So see here, this is sort of an attempt at producing this, exactly what you asked for. So we have a tensor product of these two, and we want the algebra to act on it. But this algebra acting on it, if we don't give some structure of this that depends on Z, well, it will never produce some non-contractible loops. So what we say here is that this gluing operator, what it does is it precisely tells you how twist factors should appear. Otherwise, if it was just a usual tensor product, we would not have twist factors. Twist factors and the weight of loops that surround both points. So this is sort of an attempt at what you did, but I don't think it's complete. I think that correct way of doing things is to say that to put just a tensor product like we had, so a tensor product here, and then in between a normal tensor product with, a selective tensor product that only lasts through elements here. And then what should be acted on here is not EPT-LN, but this algebra quotiented by the relations that omega to the n is z to the n times the identity, or z to the 2k times the identity, and then an equation for the contractible loops. So we should remove those. We have not proved that the two are equivalent, so we have not given this in our paper, but we believe that this is a correct way of doing things.